So in this video, we're going to be reviewing for a College Algebra Test 2. I actually have in front of us an old College Algebra exam. And so the first question that we want to answer is, let f of x equal 4 all over the quantity 1 minus x. And we're going to answer the following questions. First, we're going to find the inverse of this function. And so when we're finding inverses of functions, we're rewriting the function notation first as y. And so let's just rewrite this equation. So this equation we're going to have in front of us is y is equal to 4 minus 1, so 4 divided by 1 minus x. We're swapping our x and y's values. So wherever I see a y, I'm going to replace it with x. And wherever I see x in that equation, I'm going to replace it with y. So rewriting this, I would have x is equal to 4 all over 1 minus y. So once we swap our x and y values, we want to solve for y. So to solve for y in this equation, let's first clear our fraction. And so we're going to multiply both sides of our equation by our denominator 1 minus y. So doing so, let's distribute that x on the left-hand side. And so we would get here x minus y times x is equal to, whole point of this was so the right-hand side, that denominator would cancel, we're just left with 4. So again, our goal is to solve for y. And so we want to isolate the term that has y in it, or terms if there were more than one term. So let's subtract x on both sides of that equation. And doing so, we would be left with a negative y times x is equal to 4 minus x. So I notice we can get y by itself if we divide both sides by negative x. So doing so, we would get y is equal to 4 minus x all divided by negative x. So once we've isolated y, we're going to rewrite that as f inverse of x. So I get f inverse of x is equal to 4 minus x all divided by negative x. We can leave it like that, or if you wanted to, we could pull the negative that's in the denominator out front. I'm just going to leave it like this. So once you find the inverse function, we can check to make sure that we did everything correctly by going back and taking the composition of two functions. And when we take a composition of a function and its inverse, we should get back x. So either direction we take that composition, in this case, f of f inverse of x or f inverse of f of x, we should get back x. So show that f of x and g of x are inverses. So I believe that maybe that I was wanting that this is g of x now. We're going to let g of x be what we found to be the inverse function, f minus x divided by x. Divided by negative x. So if I wanted to take the composition f of g of x, I would be going back in here, and wherever I saw g of x, I'm replacing it with that equation, 4 minus x all over negative x. So doing so, we're going to go back to our equation, f of x, which is up here. And wherever we see an x in that equation, we're going to replace it with g of x. So doing so, we would have 4 in our denominator, all divided by 1 minus, I see an x there. So we're going to replace it with the inverse function, which was 4 minus x divided by negative x. So we need to do some manipulation here to simplify this and hopefully get out x. that we get back x. I notice I have a complex fraction, meaning I have fractions within fractions. One way to clear the fraction within the fraction is to multiply by a fancy one, and that fancy one, let's call it negative x. So doing so, we would have, well, 4 times this negative x, that's going to be negative 4x, all divided by, so I need to distribute this negative x in the denominator. So negative x times 1 is negative x minus, but I have this negative here and this negative here, so it's actually plus. And then I would have my x's cancel. I really don't need that parentheses anymore because it's not negative. And so I would have 4 minus. Sorry, let's just see 4 minus x. Let me just see something that was positive. Actually, that we're not going to distribute that negative because right here, I'm canceling that negative x out. And so I would still have that negative in front, which means I still need those parentheses there. There we go. So I noticed something was wrong because I could see when I simplified that I wasn't going to be getting x back. So that told me that I was either doing something wrong when I was doing the composition or I had gotten the answer wrong. But I was doing something wrong. I changed that negative into a positive when I shouldn't have. So because of this minus still out front, I need parentheses around that numerator when I distributed and the negative x canceled. So 4 minus x in parentheses. And so let's distribute that negative. And so we're here with a negative 4x all over 1 minus 4 plus x. And again, I shouldn't have, it's early in the morning, a negative x. I should still bring down this negative x. Again, I could see something was wrong because I wasn't getting what I needed. So negative 4x all over negative x plus x. Those cancel, leaving us with negative 4. And we get back just x. Okay, so like I had stated as I was doing the problem, I was making little teeny tiny errors while I was solving it, but in a way, maybe it was a good thing that that was happening because I knew, and hopefully you would know too, as you were working through the problem, if you weren't getting back x when you took the composition of a function and its inverse, then you're doing something wrong. And so you either need to find out where that error is, what is going on when you take that composition, or if you can't find that error, maybe going back and looking at what your inverse function was and how you solved it, make sure you got that right. So the next problem in this old exam that I gave was the following. So it states let f of x equals x squared minus 2x minus 3. And we want to answer the following questions. So we want to find the vertex of the parabola. And we want to tell is that vertex a maximum or a minimum point and why. So there's 2 different ways that we can go about finding the vertex of a parabola. One way is to do completing the square method and manipulating our quadratic formula to look like the form of f of x equals a all times x minus h quantity squared plus k. And if we can get it into this form, the vertex is equal to hk, which if you think about our translations of graphs, this minus h in here, this shifts it to the right h units. And that plus k was our vertical shift. And so this shifted it up k units. Now, if those signs change, then those things would change also. But we can see that by transformations of functions, we would get hx as our vertex, moving that vertex that was at the origin to that. The other way that we could find this is there's a vertex formula. And the vertex formula states that the x value of the vertex is negative b over 2a. And the y value of our vertex, well, we're just going to plug in what we found for x to be of the vertex into our function. If it was f of x, it would be f of negative b over 2a. So the vertex is at the point negative b over 2a, comma, f of negative b over 2a. So either way, you can find the vertex. Sometimes I ask you to put it in vertex form, and so we could go backwards, find the vertex, the point, and then plug it in for h and k up here, and we would have it. Okay, so that being said, let's go through and find the vertex. I'm going to go through and I'm going to complete the square just because I know that that's a technique that you need to know how to do. Fortunately, that coefficient in front of my x squared is 1. And so I'm going to try to figure out what I need to add to my x terms, x squared minus 2x, to make that a perfect square. So I'm going to add something there. And I'm going to subtract the same number I added there. So I'm technically adding this fancy 0. And then let me bring down my minus 3. So I'm looking for the number that I can add, the same number I can add to get negative 2. Let's just say, I don't know, c plus c equals negative 2. And whatever we find that c to be, we're going to square it and put it up here. So to get what you would add to itself, to get negative 2, let's take negative 2 divided by 2, which we get negative 1. So negative 1 plus negative 1 is negative 2. And so now let's think about negative 1 quantity squared. That would give us back 1. So I'm going to add 1 and I'm going to subtract 1, which I already have the subtraction right there, to make that a perfect square, those first 3 terms. And so these first 3 terms is a perfect square. So we have f of x is equal to the perfect square here. It was negative 1 that we multiply to give us back positive 1 and add together to give us back negative 2. So we get x minus 1 quantity squared. And then outside of that, we have negative 1 minus 3, which is minus 4. And so I can tell here that my vertex is equal to opposite sign inside. So opposite sign inside, that's going to be 1. And it's the same side outside sign, which is negative 4. So wanted to know, is this vertex going to be a max or a minimum value of our parabola shape? Well, that has to do with the coefficient a out here. Recall if a was greater than 0, our parabola faced upwards, and if a was less than 0, our parabola faced downwards. And our a value is just that coefficient in front of the x squared also. So I see that a is equal to 1, which is greater than 0. So my parabola is facing upwards, which would make that vertex a minimum point. So the vertex is a minimum point. So the next part asks us to find the x and the y intercepts if they exist, and if not, show why. So there's 2 ways we can approach this. We can look at our f of x function that we just got. And we can factor that and set it equal to 0. So we're looking at when is f of x equal to 0 to find our x-intercepts. If that was not factorable, I would use the other method where I would use the equation we just found in that vertex form. And I would set that equal to 0 because I could use my square root method that we learned earlier in this class. But I noticed that f of x factors really nicely. There are two numbers that multiply to give me -3 and would add to give me -2, and that would be -3 and +1. So our function f of x factors as x minus 3, that quantity times the quantity x plus 1. Finding the x-intercepts, we're setting that equal to 0. And so I can see that my x-intercepts are going to occur when x is equal to 3 and x is equal to -1. So it doesn't state to put the point, but I'm going to put the point. So that was 3, 0 and -1, 0. But because I didn't state, put the point, you could have just said x equals 3 and -1. The y-intercept, we find y-intercepts by letting x equal 0. So if we let x equal 0, so go back into our equation, wherever we saw an x, we're going to replace it with 0. And so we have x, so parentheses squared, -2, put parentheses where you saw that x, times parentheses -3. Dropping in 0 wherever you see an x, we are just left with a -3. So we have a point here, x is 0, y is -3. So graphing the function, we have our vertex at 1, -4. So putting our point there. We have x-intercepts at -1, 0 and 3, 0. And a y-intercept at -3. So looking at this, I get the following shape. So if this was off somehow, like maybe I found my y-intercept was down here, I would know I had done something wrong because it wouldn't give me that parabola shape. So looking at what I had gotten, it looks correct by how the shape of that graph looked. The axis of symmetry is that value where if we did a reflection across that x equals line, we would have a mirror image. And so that axis of symmetry is always through that vertex, and vertical lines are in the form x equals, and that vertical line is x equals 1. So where is the graph increasing and decreasing? So we're looking at what is the graph doing as we move left to right. And so I notice as I'm moving left to right until I get to my vertex or the x value of 1, my graph is decreasing. So I'm decreasing here. Normally, I would ask you to put it in interval notation, but it doesn't state, so you can put it in any form that you want. And so we're looking at just the x values that you're using. You're using the x values from -infinity until we hit x equals 1. Or another way to state this is x is less than 1. So I notice we're going up once we hit the vertex from left to right, starting at 1 and going to infinity. Or another way to state this in inequality notation, x is greater than 1. So from here, I said either look at the graph that you made in part C or solve algebraically to find when f of x is greater than 0. So f of x is greater than 0. This is saying my y values are bigger than 0. So looking at our graph over here, once we're less than, and this would be an open circle technically. Oops. I was afraid that was going to happen. So this should actually be an open circle here because that inequality is not including that sign. And I'm a little off on my graph. Okay, my x-intercepts was up here. I had to go through this line. Got it. Okay. It's good that I can just laugh at myself. It's good to laugh at yourself sometimes, right? Okay. Maybe not. Let's see. There we go. So again, so f of x is greater than 0. Let me load this up. When we have values from x from negative infinity to -1, we're not including union 3 to infinity. Just because I might ask you to do both ways, let's look at solving this algebraically. And so we had the equation x squared minus x, maybe that was minus 2x, I believe, minus 3 was equal to f of x. So we want to know when f of x, this x squared minus 2x minus 3 is greater than 0. So there's multiple ways that you can approach this. We could look at it in the factored form. Solving nonlinear inequalities, you want to get the inequality to have 0 on the one side, which this does. You want to then factor it and find your critical numbers. Our critical numbers are where this is equal to 0. And so this is equal to 0. Our critical numbers are when x minus 3 equals 0, so when x is 3, and when x plus 1 equals 0, so when x is -1. You place those critical numbers on the number line, and then we're testing intervals to see if we have them to be true or false. And so test something to the left of -1. So let's say x equals -2. We want to plug that back in to our function and see if that is negative or not. So when x is -2, we're wondering, is f of -2, is this greater than 0? And if so, then it would be true, and that would be part of our interval that would be part of our solution of that inequality. So you can either plug it back into the factored form and just see if it's positive or negative. And so remember that factor form we have here is x minus 3 all times x plus 1. So just think about it. If I plug in an x here, this would be -2 minus 3. So that's a negative number. And then if I plug in -2 here, -2 plus 1 is a negative number. Multiplying two negative numbers together is greater than 0. So this is true. Choose a number between x equals -1 and 3, but not one of the endpoints. So 0. Looking at f of 0. So going in and plugging in 0 wherever I see an x, I have 0 minus 3. So that is a negative number. And then I would have 0 plus 1, which is a positive number. And that is less than 0. So is this greater than 0 was our question, and that is not. It was less than 0, so this is false. And one more interval, so something bigger than 3. So if we chose x equals 4 and we plugged it in, is f of 4 bigger than 0? So again, we can look at positive and negatives. So if we plugged in -4, or we saw an x here, we have not -4, +4. We have 4 minus 3, which is a positive number. And then 4 plus 1 is also a positive number. Positive number times a positive number is greater than 0. So that is a true statement. It was strictly greater than, so it's everything smaller than -1 and everything bigger than 3. So we can state this, our solution. Well, it's up here also, and I'm not going to write it again. So -infinity to -1, parentheses around that, and then union parentheses 3 to infinity. So looking at the next problem, we have g of x is equal to x squared plus x minus 6. That polynomial is in the numerator, and then that is all over the x squared minus x minus 6. So answer the following questions. We want to find the vertical asymptote. So vertical asymptotes, recall, are where our denominator, values that set our denominator equal to 0, but also not also our numerator. Normally that's the case. If the degree of our denominator, if we had like factors, had a higher multiplicity than our numerator, then it would have an asymptote there. Okay, so I want to factor this. So let's factor both the numerator and the denominator. So x squared plus x minus 6, I notice can factor as x plus 3 all times x minus 2. So factoring my denominator of x squared minus x minus 6, I notice that's x minus 3 all times x plus 2. So these are not like factors in the numerator and denominator. They almost look like it, but they're not. And so we want to set our denominator equal to 0. And those are going to be the values where we have our vertical asymptote, or in this case, asymptotes. And so x minus 3 is 0 when x is 3. And x plus 2 is 0 when x is -2. So make sure that you write them as x equals the number, because these are equations. And so if you just put 3 and -2, I would probably knock some points off there when I was grading, because you're just giving me a number and not an equation. Okay, so from here, the next question says, does g of x have a horizontal or slant asymptote? And what is the asymptote? So it depends for horizontal asymptote and slant asymptote, which is also called an oblique asymptote, which your book uses that terminology, oblique. There's going to have one or the other, and that has to deal with the degree of our rational function. And so the degrees are the same. So the degree are the same, then we have a horizontal asymptote. And that is going to be at y equals the leading coefficient of the numerator. So the leading coefficient is that number in front of the variable raised to the highest power, which is 1, divided by the leading coefficient of the denominator. And so looking at the variable to the highest power, which is x squared, and we're looking at the coefficient in front, doesn't show 1, so it's 1. So we have a horizontal asymptote. Again, this is an equation. It's a horizontal line. So write it as y equals 1. So to find the x and y intercepts, So x-intercepts, we let g of x equal 0. And so doing so, we have x squared plus x minus 6 all over x squared minus x minus 6 equal to 0. Clear your fraction, multiply both sides by your denominator, x squared minus x minus 6. So x squared minus x minus 6. So that would clear our denominator. Anything times 0 is 0. And so we would get, I'm going to factor the numerator just so we can have it fall out nicely at first or right away. So x plus 3 times x minus 2 is the factor of our numerator is equal to 0. So I have x-intercepts when x is -3 and when x is 2. These are actually points and not equations. So -3, 0, and 2, 0. The y-intercepts are usually the easier ones to find. You're plugging in 0 wherever you see an x. So we're looking at g of 0. So I would get 0 squared plus 0 minus 6. So I'm left with -6 in the numerator. And all over 0 squared minus 0 minus 6. So all over -6 in the denominator, which is 1. So we have a point here at 0, 1. That's our y-intercept. So from knowing where our vertical asymptotes are, where our horizontal asymptote is, where our intercepts are, we're pretty close to graphing this. And so let's plot our asymptotes first. So we had x equals 3, x equals -2. So I'm going to put dotted lines to notate that that's where my asymptote is. It's not really part of the graph, though. So vertical line at x equals -2 and x equals 3. And then we have a horizontal asymptote, so a horizontal dotted line, just to denote that we have one there at y equals 1. So plotting my points, we had some points at -3, 0. And at 2, 0. And a y-intercept at 0, 1. So I can actually tell what the shape of that graph is going to look like inside between those two vertical asymptotes, x equals -2 and x equals 3, just because of where the points are. So my multiplicity of my zeros is 1. It's odd, it's going to cross, it's not going to touch. And so knowing that where this vertical asymptote is, I know I'm going to have to be decreasing. Hit my y-intercept, hit my x-intercept, continue decreasing, and then hug those vertical asymptotes on each side. So x equals -3. It technically, well, because of where the asymptotes are again, my guess is it looks like this shape on the left of x equals -2. But let's just make sure, let's choose one point to the right. I could choose one point in between -3 and -2, but that's a fraction. So let's go to the right. Let's go in and plug in -4 into our equation. And so if we looked at g of -4, so our equation was x squared plus x. So I'm going to put parentheses -6 all over x squared minus x minus 6. So putting parentheses where I'm going to drop in the -4. And then let's quickly simplify. So -16 quantity squared is 16. 16 minus this 4, that's 12, and 12 minus 6, that is 6 in the numerator. Denominator, I have -4 quantity squared, that's 16. This is really plus 4, so that's 20. And 20 minus 6, that is 14. So notice this is a positive number. It's going to be less than 1. It is less than 1. 3/7. So we have this value over here. Oops, up here. So what I had determined it was going to be was where it was. Looks like this. Okay. I was going to say it looks like it's symmetrical, but it really isn't. So let's go and see what's happening on the right-hand side of our vertical asymptote x equals 3. My guess is that the shape is going to look like this just by where my asymptotes are. But we can state that really quickly by let's choose a point to the right of x equals 3. So how about x equals 4? And let's just show that we're above the x-axis. And if we're above the x-axis, that has to be the shape that I just gave you. So let's look at g of 4. So going in and plugging in 4 wherever you saw an x in our original function of g of x, and putting parentheses wherever I see an x, and then I'm going to go in and drop in 4. Okay, so we got 4 squared plus 4 minus 6 all over 4 squared minus 4 minus 6. Simplifying, I get 16 plus 4 is 20. 20 minus 6 is 14. All over 16 minus 4, which is 12, minus 6, which is 6. This is greater than 1, which is up in here. So what I did was correct. So I just wanted you guys to be aware that, recall, our graphs can never cross a vertical asymptote, which if you think about our domain of our rational function, we have to worry about values which set our denominator equals 0, and we have to exclude those. And so our domain of this rational function, x could not be -2 and x cannot be 3. So we can never cross the vertical asymptote. We can cross a horizontal asymptote, and in this graph you can see that our point, our y-intercept 0, 1, was going through or touching our horizontal asymptote y equals 1. So we are allowed to cross a horizontal asymptote. We can cross also a oblique or slant asymptote. And if you were trying to find out where that was, you would set the equations equal to each other. So technically, my equation for my horizontal was y equals 1, and my g of x is equal to this x squared plus x minus 6 all over, again, x squared minus x minus 6. So set your g of x equal to 1 and solve for x. And if you go through and do that, we should get that x is equal to 0. But I'm gonna just move on. I just wanted to state those couple of things before we continue on and doing problems on the exam. The other thing I kind of wanted to state is, there was a question when the video was paused, is how do I know that it's this shape in between these two vertical asymptotes like this? So sometimes what's in between those two vertical asymptotes could kind of look like a parabola shape. It could have turned back around. The thing is, I knew where my x-intercepts were, and I knew that I did not have an x-intercept between this -2, x equals -2 and 0. So it would be impossible for this to turn back around and cross that x-axis there because there's no x-intercept. And so knowing where my vertical and horizontal asymptotes were, I knew that that had to be that shape in between. And if you're not sure, just plot like 1 or 2 more points. Usually seeing 2 points on each side of a vertical asymptote, you can kind of tell what's going on. So you can always plot a couple extra values. So the next question on this exam, h of x is equal to x to the fourth minus 4x cubed plus 9x squared minus 20x plus 20. Use the rational zero theorem. What are the possible rational zeros of h of x? So rational zero theorem, that was where we look at the p divided by q. P are factors of our constant. So numbers that go evenly into that constant, in this case 20. So plus or minus, or plus and negative, positive and negative, that's probably better to say. 1 goes into 20, 2 goes into 20 evenly, 4 goes into 20 evenly, 5 does, 10 does, and 20 does. So now looking at our q values, q is factors of our leading coefficient, in this case is 1. So we have positive and negative 1. So it's nice when q is 1 because when we look at p divided by q, you're just dividing every number in p by positive and negative 1, which would just give us back what p is. So 1, 2, 4, 5, 10, and 20. So these are, if h of x had a rational zero, it would have to be one of these numbers. And so this narrows down our list. And so now let's just try using synthetic division by the zero remainder theorem. If we get a remainder of 0, we know that this would be a 0 of our polynomial. And so let's try 1, put it up in this kind of box shape. We write down the coefficients of our polynomial. If there was any term missing, we would put 0 as a placeholder. Make sure that your polynomial is in descending order of powers. So x to the fourth, we have a 1, and x cubed, we have -4, x squared, we have 9, x is -20, and our constant is 20. So on a horizontal line, write 1, -4, 9, -20, and 20. This is where we bring down our first number 1. 1 times 1 is 1. Put that number, that multiple, underneath the next number. Sum those up. So -4 plus 1 is -3. Take that and multiply it by this number in our box. So -3 times 1 is -3. 9 minus 3 is 6. 6 times 1 is 6. -20 plus 6 is -14. 1 times -14 is -14. This is not equal to 0. So 1 is not a 0 of our polynomial. While I'm going through this, I'm going to be looking for my upper bounds and lower bounds. If I plug in a positive number up here in this box and the bottom row is all positives, then it's going to be an upper bound. This is not a row of all positives. So I know that it's not an upper bound, so I can choose a number that's bigger than that. So again, putting my coefficients in a horizontal row. And let's bring down our first number. So 1, and then multiply it by the number in our box. So 2 times 1 is 2. -4 plus 2 is -2. 2 times -2 is -4. 9 minus 4 is 5. 2 times 5 is 10. -20 plus 10 is -10. 2 times -10 is -20. And this gives me 0. So I'm really happy when I get a 0 there, because that means I found what 0 was. So x equals 2 is a 0. Which my guess is I'm going to ask you also how to factor this. And so because x equals 2 is a 0, I know that x minus 2 is a factor. So I want to break this down. I want to find the other zeros. But notice right here, this bottom row, that is actually, if I had done long division, that was my quotient. So this is also a factor. We start 1 degree less, and we had a degree 4 polynomial. So this is degree 3. These are the coefficients starting at degree 3. So that would be 1x cubed. So x cubed minus 2x squared plus 5x minus 10. So I can continue and use synthetic division if I want, or if you see other ways to factor, go ahead and do that. If it was quadratic, I would probably factor it right away. The thing is, I noticed while I wrote this down, there's 4 terms and it looks like that this factors by grouping. So for instance, let's just do it up here. So x squared minus 2x squared plus 5x minus 10. So if I group the first 2 terms together, x squared minus 2x squared, I could factor out an x squared from both of those terms, and that was an x cubed up here, x cubed. So I can factor out an x squared from both of those terms, and I would have x minus 2 left. So notice 5x minus 10. We can pull a positive 5 out of both of those terms, and we would be left with x minus 2. We want what's inside that parentheses to be the same. So if we factored out x minus 2, we would be left with x squared plus 5. So notice x minus 2 is another factor. So x equals 2 is a 0. Well, we had x equals 2 is also a 0 up here. So this is a 0 with multiplicity. 2. I want to look also, though, at when is this x squared plus 5 equal to 0? Well, if I subtracted 5 on both sides of the equation, I would have x squared equals negative 5. I take the square root of both sides. This is x equals plus or minus the square root of negative 5. So x is equal to plus or minus. Square root of negative 1 is I. So I root 5. So we found all the zeros of the polynomial. It didn't state just to find all the real ones. So our zeros are x equals 2. Again, multiplicity 2. And plus or minus I root 5. So it asked us what the zeros are. I just stated them up there in the box. Rewrite h of x as the product of linear and or irreducible quadratic. So this quadratic factor that we had up here, x squared plus 5, that is irreducible over the real numbers. So h of x, this is equal to x minus 2 all times x minus 2 all times x squared plus 5. So the next piece wanted us to find the end behaviors of our graph. I just write h of x over here so I don't have to keep going up and seeing it. So h of x was x to the 4th minus 4x cubed plus 9x squared minus 20x plus 20. So recall the n values of our quadratic, not quadratic, our n values of a polynomial have to deal with our leading term. So that is the variable raised to the highest power and the coefficient. And so what's going to determine the end behaviors of our graph is this x to the fourth. So think about it with kind of some logic. So if I'm going to negative infinity, and one way we can write this is the limit is x is going to negative infinity of x to the fourth. So if I went in here and I plugged in negative numbers wherever I see an x, as that was going to negative infinity, and I raised that to the fourth power, this is going to be a positive number. And so this tells me that this is going to shoot off to positive infinity. So it's shooting upwards like this. So looking at the limit as h of x is going to positive infinity, again, I'm just looking at x to the fourth. Well, if I plug a positive number in and raise it to the fourth power, I'm also getting a positive number. So this is going to be positive infinity. So my end behavior again is shooting, in this case, upwards as we go to infinity. So the next question in front of us, let f of x equals log base 2 of x minus 2. And then outside of that parentheses, x minus 2 is plus 1. So we can graph this, think of it by using transformations. If we were looking at transformations of y equals log base 2 of x. So knowing the general shape of what our log looks like is helpful. Our base is greater than 1 of our log. And so our graph looks similar to this. So it's going to cross at 1, 0. And we have a vertical asymptote at x equals 0. And so I can tell that this minus 2 in here, this is going to move my graph to the right. Two units. And this plus 1 in here, this shifts it up 1 unit. So I can take this point that's always on my graph of a log base b of x, which is at this 1, 0. And I can now use my transformation. So if I move that to the right 2 from there and up 1. So it's going to look like that right there. And my vertical asymptote that was at x equals 0 is now going to become a new vertical asymptote at x equals 2. And so I would have some sort of graph that looks like this. I could technically, if I wanted to, find where, and I'm going to have to look at it, based off the graph of f of x, solve for where f of x is greater than 0. So let's look at when our graph is equal to 0. So let's look at when is log base 2 of x minus 2 plus 1 equals 0. Trying to find my x-intercept. Well, if I subtract 1 on both sides, I would get log base 2 of x minus 2 equals -1. Let's rewrite this in exponential form. Our exponential form is going to be, our base is 2. Raise it to what's on the other side, -1. is equal to this argument here, x minus 2. Well, 2 raised to the negative 1 power, we can make that exponent positive by bringing it down to the denominator. I get 1 over 2 is equal to x minus 2. So we can get x by itself by adding 2 to both sides of our equation. So x is equal to 2 plus 1/2. Getting a common denominator, I could multiply 2 by 2 over 2, so that's 4/2 plus 1/2 is 5/2, which is the same thing as 2 and 1/2, which you can see by 2 plus 1/2. So this right here is at 2.5. So what is f of 6 and what is the point on the graph? So f of 6, we're just going to go in wherever we saw in x and f of x. Just going to erase this for a sec. So here's our equation. We're going to go into f of x and we're going to plug in 6 wherever we see an x. So we have log base 2 of 6 minus 2 plus 1. So this is equal to log base 2 of 6 minus 2 is 4 plus 1. So let's evaluate our log. This is saying, what am I taking my base to? What am I raising 2 to get back my argument of 4? Well, 2 squared is 4. So my exponent would be 2. Logs are just exponents. So I have 2 plus 1, which is 3. So I have a point when x is 6, y is 3. So the next one states, find when f of x is equal to 4. So this is stating what's fine when log base 2 of x minus 2 plus 1 equals 4. So to solve log equations, we want to isolate our log. So we want to subtract 1 on both sides of our equation. So doing so, we get log base 2 of x minus 2 equals, well, 4 minus 1 is 3. Once you rewrite your log equation, so it's a log equals a constant, we can rewrite this in exponential form to help us solve. So we're taking our base of our log, which is 2. We're raising it to the other side, which is 3. So 2 cubed is equal to our argument, which is this x minus 2. So let's simplify. 2 cubed is 8. 8 is equal to x minus 2. So let's add 2 to both sides. We get x is 10. So what is the point? So when x is 10, our y value is 4. So in this case, our point is 10, 4. So based on the graph of f of x, solve for f of x is greater than 0. And so I needed to know, and I saw this, that's why I went and found the x-intercept. So looking at this, I know my x-intercept was at 2.5. Notice that our graph is above the x-axis on this piece where we're bigger than 2.5. So values which would give me f of x is greater than 2.5 are when x is bigger than 2.5. Or I can stay in interval notation, parentheses 2.5 to infinity. So it now states find f inverse of x. So let me write f of x down again. F of x was our log base 2 of x minus 2 plus 1. So this is f of x. I'm going to write this as y equals because we're going to have to do that anyways when we're solving for the inverse function. And so solving for inverse function, we're swapping our x and y values. And then once we swap them, we're solving for x. And so swapping my x and y values. So I would get here x is equal to log base 2 of y minus 2 plus 1. I think I might have just stated that we're solving for x, but we're solving for y. I stated that, that's what I meant to say. So let's isolate the term. Let's isolate our log first. So we can do that by subtracting 1 on both sides of our equation. So if we subtract 1 on both sides of our equation, we get x minus 1 is equal to this log base 2 of y minus 2. That's what I wanted. So let's see. So let's go back. Let's rewrite this in exponential form. So I have isolated my log. Now I can write this in exponential form. So I'm taking my base, which is 2, raising it to the other side of my equation, which is x minus 1. This is equal to my argument, y minus 2. So our goal is to solve for y. We're almost there. All we have to do now is add 2 to both sides of our equation, and we would get y by itself. So y, which is going to end up being our f inverse function, is equal to 2 raised to the x minus 1 power, and then plus 2. So that was the rest of that problem, but I could see myself asking you guys, what is the domain of f of x? So if I look at the domain of f of x, recall when we're looking at the domain of logs, we have to look at our argument, in this case, x minus 2. And we can't have a log of a negative number. And so you would take what this argument is, x minus 2, and we know that that argument has to be positive. It has to be greater than 0. So this is a linear function or linear inequality. So I could add 2 to both sides. So x had to be greater than 2, which if I looked at my graph, after graphing it, my vertical asymptote was x equals 2, and it had to be bigger than that. So that would be my domain of f of x. My range, so I might ask you the range of the function. The range, I'm hitting all my y values. So it's negative infinity to infinity. And this is for f of x. But then I might ask you, okay, what's the domain and range for your inverse function? So recall when we were solving these, we were swapping our x and y value. So x is our input, was our domain, y is our output, our range. If we swap those, the inverse functions has swapped. The domain is actually its range, and the range is actually its domain. So the domain of f inverse of x, this is x values. It's going to be all real numbers, negative infinity to infinity. The range of f inverse of x was the domain, which was x greater than 2. But this is a range, so it's not x values, it's y values. So y is greater than 2. So You should know how to find the domain and the range of a function and its inverse, but you also should be able to find the domain of a logarithmic function. So the last question on this exam is solving exponential and logarithmic equations. So our first equation is 2 cubed is equal to 2 raised to the x squared power times 2 raised to the 5x power. I notice that I can manipulate both my bases to be the same. If we can manipulate the bases of our exponentials to be the same, so we have some, let's just call it a function. Let's say b raised to some function g of x. We manipulate it to be that equals b raised to some function f of x. Then we can state that our exponents are equal to each other. G of x equals f of x. So I can manipulate these bases to be the same. The problem is on the right-hand side, I have 2 raised to the x squared power times 2 raised to the 5x power. I'm going to use rules of exponents here, that if I have the same base and I'm multiplying, the rule of exponents is you have the same base and then you would add your exponents. So b raised to the n power times b raised to the m power is equal to b raised to the n plus m power. So rewriting this equation, I would have 2 cubed equals 2 raised to the, using that rule of exponents, x squared plus 5x. So we manipulated the bases to be the same, so I can set the exponents equal to each other. So 3 has to equal x squared plus 5x. Now looking at this, I would solve for x. So I could subtract 3 on both sides. So I get x squared plus 5x minus 3 equals 0. Unfortunately, I can't factor this, but I can use the quadratic formula. So I know x is equal to negative b, so negative 5, plus or minus the square root of b squared, 5 squared is 25, minus 4 times a, so 4 times 1 is 4, times c, so negative 4 times, because it's minus 4ac, so negative 4 times negative 3, this would give me plus 12, all over 2 times a, 2 times 1 is 2. So we get here x is equal to negative 5 plus or minus the square root of 37 all over 2. So the next equation we have is log base x of 64 equals negative 3. So really with these logarithmic equations, if we can get it in the form of log equals a number, rewriting these in exponential form is really helpful. And so we can take this, our base of our log is x. And so we're going to take our base, which is the base of our exponential, is raised to the other side, which is negative 3, equals our argument in this case, which is 64. So let's rewrite that negative 3 exponent as positive. We can rewrite it as 1 over x cubed equals 64. I could clear my fraction by multiplying both sides of my equation by x cubed. So I would get then 1 is equal to 64x cubed. Can get x cubed by itself by dividing by 64. So I have x cubed equals 1 over 64. I can think of this now as taking the cubed root of both sides to get rid of that x, the cubed on the x. So I have the cubed root of x cubed equals the cubed root of 1 over 64. So we get x is equal to can break it down as the cubed root of 1, which is 1, all over the cubed root of 64. So there is a number I can cube to get back 64, and that would be 4. So x in this case would be 1/4. I guess from this point right here, we could have approached it a little differently. If you remember, power to power is multiplication. You could have technically raised this. We want this to be an exponent of 1. I could have raised both sides to the negative 1/3 power. So negative 3 times negative 1/3, that would give me my positive 1 exponent. This would have been x to the first equals, we could make this exponent positive by bringing down 64 in the denominator. So this would be 1/64 to the 1/3 power. Rational exponents, you can rewrite the term as a radical. So this would be 1 over the cubed root of 64. So x is 1/4. I don't know if that was easy or not, but you could have approached it a little differently. So the following, we have log base 3 of x minus the square root of x minus 2 equals 2. So we have a log equals something. So we could rewrite this in exponential form. So we're taking the base of our log is the base of our exponent. What this was equal to of our log is the exponent. So this is 3 squared is equal to our argument of, and that is what you were taking the log of, which is the square root of x minus 2. So I can rewrite 3 squared as 9. So 9 is equal to the square root of x minus 2. Get rid of the square root. I could square both sides of my equation. So 9 squared is 81 is equal to square root squared cancels, leaving us with what's underneath the radical, which is x minus 2. So if 81 equals x minus 2, if we add 2 to both sides of our equation, then we can get x by itself. So x is equal to 83. So I don't know if you remember, but if we raise both sides to an even power, we could get what are called extraneous solutions. So we have to go back and check. The other thing that you have to be careful of, and I should have been careful on the other one too and stated it, we can't have a log of a negative number. We can't have a log of 0. It's undefined. So we need to make sure that that doesn't cause that. And back on the other example, we could not have our base has to be greater than 0 and it can't be 1. And our base was greater than 0 and wasn't 1. So we were okay on that one. Okay, so going back here, let's just check it. We must check. So is log base 3 of the square root, plugging in 83 for x, of 83 minus 2, is this really equal to 2? Well, log base 3 of the square root of 81, is that equal to 2? Well, we can simplify a little more. Log base 3, square root of 81 is 9. Is that equal to 2? Rewriting in exponential form is 3 squared equal to 9. And it is. So we're good. And we found that our solution was x equals 83.